Okay, sorry about it. It's this. Okay, so I think you all know this, so this is just to remind you that where we are. So the posters are going to be here next week, just outside Levin. Well, all the 519 students are going to be here. Hopefully the 419 students will also be here. I think it would be interesting to look at what others are doing. And you do have a lot of time until the final report, so I'm assuming that this will be some kind of an intermediate report. You also know that we have an exam. Everything has been already put on the webpage. Questions? Okay, so where are we? So we've been talking about naive Bayes, and then we use naive Bayes as a way to introduce semi-supervised learning. If you remember, we were given 10 examples. We try to make predictions, whether it's N or V, given these N examples. And what I show here is how we did this. Basically, this is a run of naive Bayes. And given that, the question that we ask is, what happens if we are given other examples, but they are not labeled? We suggested several algorithms. That we called, basically, there were algorithms that said, well, I know how to predict on examples because I already have a model that I learned for my 10 examples. I can predict on the 100 examples, label, and then add these examples into my training set. We thought a little bit about it, and you agree that this may not be the best idea. We want to be a little bit more selective in which examples we're going to add to the training set. And in fact, this is what you're playing with also in experiment 2 in the homework. So that was one option. The second option, that is also an extra credit in your homework, is to think about it in the following way. To realize that when we compute the naive Bayes probabilities and make prediction with naive Bayes, we actually don't need the examples to be labels with integers. We can say that an example is 0.8 n and 0.2 v. So if you have a table with examples and labels, and rather than 0, 1 as labels, you will have fractions, nothing is going to matter, right? You're going to do the same computation. And this is a more general way for dealing with this problem. And as we'll see, a very general way to run semi-supervised or unsupervised learning in general. So the idea here is this, is just written in these last few lines. So we keep fractional labels, and we deal with that. And that's going to be the way we're going to do semi-supervised learning in this case. Okay, so then we ask the question, once we summarize these algorithms, we ask the question, what happened if instead of the 10 labeled examples, we actually have 0 labeled examples to start with? This is where we ended last time. And this is going to be an important question that gives rise to an important algorithm that we're going to call the EM algorithm. Basically, the idea says, do as you did with the 10 examples, only that rather than initializing your model with the 10 examples, just guess. So remember, what do you need in order to have a model? You need all the conditional probabilities, P of xi, given a label. and you need P of V and P of N, the two priors. Once you have these, you can run your algorithm, right? Before you initialize these parameters with the 10 examples, now I'm suggesting guess continue in the same way. What we're going to do now is we're going to actually develop this algorithm in a slightly simpler case. We're going to call this an EM algorithm, but basically you know the algorithm already. It's essentially the naive Bayes algorithm that you're running, that we ran here, that you're running in homework 4, with the exception that you initialize it with a guess. Questions? Okay, so let's step back and talk about EM in more general. So EM is not a single algorithm, it's a family of algorithms because it's determined by the probabilistic assumptions. We have played here with the naive Bayes assumption. You can run the EM algorithm with other probabilistic assumptions, and I'm going to give an example a little bit later today. So it's really a class of algorithms. We use it as a way to estimate the probability distribution when we have missing data. So again, we have these 100 examples that do not have labels. That's the scenario where you want to use EM. It requires an assumption on the underlying probability distribution. Otherwise, we don't know what to do, and nothing is going to work. And it's very sensitive to this assumption. So if you think that the data was generated by probability distribution P, but actually it was generated by a very different probability distribution Q, it's not going to work. It turns out that it's actually a pretty robust algorithm, and once you make sensible assumptions, it's actually a very, very good algorithm. In general, it doesn't converge, but rather converges to a local maximum of the maximum likelihood function. But as I said, once you make good assumptions, it's surprisingly a very good algorithm. So let's start by motivating it with the following example. So I have 3 coins. I'm going to call one of them coin 0. The probability of head is alpha. And then the other 2, coin 1 and 2, with probability of head P and Q. Now, we can think about multiple coin tossing scenarios. Here is one. I'm tossing one of the coins 4 times. This is what I observed. And the question is, which coin is more likely to produce this sequence? Now, I didn't tell you what's the value of P, Q, and alpha, but you can still give me some property or some rule of how would you choose whether it's P or Q or alpha, given that you see the sequence. Suggestion? Yeah, go ahead. Yeah.
Yeah, I think you would assume that it's the highest Q or alpha because you can expect the most number of hits to be highest.
Why highest? I think you have the right idea. So what's your guess for the probability of the head now?
I would say 3/4.
3/4. So not necessarily the highest, but the closest to 3/4.
Okay, yeah.
Because if one of them is 0.8, one of them is 0.9, you'll probably choose the 0.8. Because maybe 0.8 would have led to 4 heads. Okay, so you know what to do when you have this scenario. That's the easy one. Here is the second one. First of all, I'm tossing coin 0. If it's head, I'm tossing coin 1 multiple times. Otherwise, I'm tossing coin 2 multiple times. And that's what I got. So what I'm showing here is the value of coin 0 in red, and then the additional coin tosses in blue. And I did this multiple times. So now, the question again, estimate the most likely values of P, Q, and alpha. What do you think is the most likely value of alpha here? Suggestions, yeah? 3/5. So you look at alpha. There are 5 tosses of alpha. 3 of them are head, 2 are tails. 3/5 is our estimate. Everyone agrees? And you can do the same thing for 1 and 2. You just have to figure out which of the blue H's and T's belong to 1 and which belong to 2, right? And you can do this because I colored the value of 0 in red. So you know which of the blue belongs to the first coin and which to the second coin. Questions? Okay. So again, you know how to do this. Here is the third scenario. I'm, again, tossing coin 0. If it's head, I'm tossing coin 1 multiple times. Otherwise, I'm tossing coin 2 multiple times. And now I observe this sequence with the difference that now I don't show you the value of coin 0. Okay? Same scenario, missing variable, missing label if you want. The red one isn't shown. And now the question is, estimate the most likely values of P, Q, and alpha. Suggestions? At least you see that it's different and potentially harder. You can think about it this way. So it's really kind of like the naive Bayes model, generative model. First of all, I generated coin 0, values from coin 0. Given coin 0, I show you just 3 tosses. Actually, there were 4 tosses. I tossed another coin based on the conditional probabilities of either coin 1 or coin 0, or coin 2, depending on the value I got for coin 0. So that's the model. And that's, hopefully, you see it's a harder problem than what we had before. And the question is, what are we going to do? Okay, so the reason you don't immediately have a solution is that it's actually a hard problem. There's no known analytical solution to this problem in the general case. You have to add some more assumptions so that there will be an analytical solution. So we don't know how to compute the parameters that maximize the data. What we're going to give is we're going to give an iterative algorithm that converges to a local maximum of the likelihood function. And as I said, in practice, a really, really important and a good algorithm. Throughout this discussion, think about the naive Bayes problem that we just solved last time with the 10 examples as a guess, or with the no examples as a guess. That's what we're going to do. So what is the intuition? Had we known which of the data points came from coin 1 and which came from coin 2, everything would be easy. Everyone agrees? Yes, no? Yes. Okay. So basically, we're going to do this, right? It's the simple maximum likelihood estimation that we did for the coin, right? That's our solution if we know the label of the coin, the name of the coin. Instead, what we're going to do is we're going to use the following iterative approach. We're going to guess the probability that a given data point came from coin 1 or coin 2, which is just like when you guessed that the previous example came from N or from V. Remember? Exactly the same thing. Now that I have this guess, I can compute the most likely value of the parameters. I know. I have a label for each example. I know whether it's N or V. I know whether it's coin 1 or coin 2. Now that I can compute the most likely value of the parameters, I can compute the likelihood of the data given this parameter, given this model. And I can start again. I can re-estimate the parameters again, figure out where each coin came from. Basically, I'm learning the model again, and I'm making predictions again. So again, think about going back to the naive Bayes problem. I started with some labeling, N and V, next to each example. It doesn't matter now where it came from, whether it came from 10 examples or whether it came from my guess. Once I had that, I could compute a prediction for each model, for each example. I could learn a model. Once I have a model, I can re-estimate and label again all the data. I'm going to get something else. So basically, the interplay here is if we have labels, we can generate model parameters. If we have model parameters, we can generate labels. Once we have these, we can compute the likelihood of the data and go back to estimate model parameters, which are equivalent to labels. And we're going to iterate this process. OK, so let's do this in the case of the coin, which is actually simpler than the naive Bayes. So for a minute, I'm going to assume that I know the parameters of the model. I know P, Q, and alpha. I'm putting tilde on them. These are my estimates of P, Q, and alpha. And now I want to look at, given an example, what is the label of the example? Which coin it came from? So I'm going to use this PQ and estimated or guessed PQ alpha to label the observed tosses. And then I'm going to use it to estimate the most likely parameters and so on. So here is my notation in the next few slides. I have n data points. In each one, I have m tosses, out of which hi heads in the ith data point that I'm going to call di. OK, so I have a data point di. What's the probability that it came from coin 1? That's what I'm asking. What is the label of this data point? This is called in the EM algorithm the expectation step. That's the E of the EM algorithm. That's the probability P1I is the probability that the ith data point came from coin 1. The probability of coin 1 given di. Using Bayes' rule, it's the probability of di given coin 1 times P of coin 1 divided by P of the data. P of coin 1 is alpha. P of the data, given that it came from coin 1. Coin 1 is the one with P, probability for head. So it's P to the H, 1 minus P to the M minus H. OK? And I'm dividing by the probability of the data, which is the sum of came from coin 1 or came from coin 2. OK? So that's the fractional label, right? That's the probability that this data was going to be labeled coin 1. So again, think about the NV from before. It's the 0.8n, 0.2v case. Now that I have this, I'd like to compute the likelihood of the data. This is a little bit harder part. There's going to be a little bit of math in doing it, and I'm going to tell you when, if you don't want to, you don't need to dive into the math. The important thing is going to be what's the algorithmic implication of this. I want to maximize the log likelihood of the data over these endpoints. This is the log likelihood of the data, sum over the endpoints, the log P of di given the parameters. Now, I don't know the coin's name. It's supposed to be part of the data, but it's not. It's missing from the data. So what I'm going to do is I'm going to marginalize over it. Marginalize is a term in probability that you're already supposed to be familiar with. Basically, what I'm going to do inside this, I'm replacing P of di by sum over y, could be 0 or 1, should have been 1 or 2 here, sorry. The name of the coins are 1 and 2. P of d and y given the parameters. Now, mathematically, this is a little bit difficult here because the sum is inside the log. It's hard to do log of sums. Logs like to have multiplication inside them. And therefore, computationally, what we do here, and this is the key mathematical step in the EM algorithm, instead of maximizing the log likelihood, which is hard to do, we're going to maximize the expectation of the log likelihood over the coin's name, over the Y. So really, this is what's happening here. I'm going to explain it in words and then explain it in math. Y is one of our variables, but it's not observed. It's a missing variable. It's the label that we don't see. So we cannot just use the complete data log likelihood that we've done, say, when we did naive Bayes for text earlier. Instead, we're going to use the expectation of the complete data log likelihood under the distribution of Y to compute this. This is another way of saying exactly the same thing. We're thinking about this expression, log, the log likelihood, log of the probability of D, given the parameters, as a random variable that depends on Y, the value of the coin. And we are dealing with the expectation of this random variable. Now, the justification comes here, where if you want to follow, you can see that there's really nothing mysterious here. This is just writing this expression. The second line is the expression that I've written before. Now, if you really think about it, what you have here is sum over the values of Y, something times P of Y, which by definition is the expectation according to Y of this something. So I'm writing it here, log expectation according to Y of this expression. Now, the next thing is to realize that, when the log of the expectation is actually larger than the expectation of the log. And the reason is that the function of log is concave. I'm writing it here, which means that if you look at the function itself, it's always above the average of points that you take. You take this point, and you take the average, it's going to be below the function. And that's the reason for this inequality. But really, you don't necessarily have to care about it. What you care about is that that's how we do EM. We maximize the expectation of the random variable, which I'm now writing here. So the expectation of the log likelihood is the expectation of this variable. And now I'm just spelling it out. What does it mean, expectation? It means with probability P1I, which I computed before, I'm writing 1 here. With probability 1 minus P1I, I'm writing 0 here. Okay? And I know how to write these probabilities. Again, the algebra doesn't matter. Since I'm going to maximize this, some of the constant terms do not matter. The important thing is that I have this sum here that comes from the expectation. And again, the details of the math are there if you want to follow it. The important thing is that I got this sum, which I'm rewriting here. So the expectation of the log likelihood is the sum over two components. The first one has P1I, and the value of the coin is 1. The second one is 1 minus P1I, and the value of the coin is 0. And we know how to compute these probabilities. The first coin has alpha, P to the H, 1 minus P to the M minus H. The second one has 1 minus alpha, and the Q's, Q to the H, 1 minus Q to the M minus H. So we can just take log of these components. So the math is very similar to the math that we've done when we did it with text, only that there is a little bit of cheating that goes through this inequality. Really, I had sum inside the log, and in order to pursue with the math, we just move to dealing with expectations. Okay, so what have we done? So now I have an expression here for the expected likelihood. And now I can derive new parameters. So once I have an expression for the likelihood of the data, just like we did before, I can ask, okay, so what are the parameters that maximize this likelihood? Okay? And I have three parameters here, alpha, p, and q. And I'm going to differentiate this expression relative to each one of them and get the new parameter. So now look at it here. This is the last two lines is what you want to care about. Let's think about alpha. If you care about maximizing alpha, alpha appears here, and alpha appears here. The rest is going to disappear. The same thing, look at where p appears in this top part. This part is going to disappear, and the same thing for q. So that's what I'm going to do here. So I'm differentiating relative to alpha. As I said, almost everything disappears. What you get when you differentiate is sum over all data points, p1i divided by alpha, 1 minus 1 minus p1i divided by 1 minus alpha. I want to equate this to 0, and that's what I get. When I equate it to 0, I get that alpha is the sum of the p1i divided by n, the number of data points. Now, before we continue, let's see if this makes sense. So what is p1i? So p1i was the label that we gave the data. Let's go back here. This was the basic step, which we called the expectation step. So we're looking at the data point, and we're asking, which coin did it come from? P1i is the probability that it came from the first coin. Okay? So does it make sense to you that my estimation, my estimate for alpha is the sum of the P1i over all data points divided by n? Let's assume for a second that the PYI are extreme. There are only zeros and ones. So what is P1, sum of the P1i? What's the interpretation? Any attempts to guess? So let's assume you had n points. 17 of them came from coin 1. What will be your estimate for alpha? Hopefully 17 over n, right? Because alpha is the selector that we had at the beginning. You toss a coin that gives us head with probability alpha. If you got head, you choose the first coin. So basically, if P1i is 0 and 1, it basically counts how many times you use coin 1, which is, so this divided by n should be alpha. Agree, disagree? Not clear? Any questions on this? Okay, and the same thing would happen if P1i is a fraction. Right? So again, you're asking for each data point that you see, rather than saying, well, it came from the first coin or the second coin, you can say, with probability 0.8, it came from the first coin, with probability 0.2, it came from the second coin, and you're summing over these fractions. So the sum of these head fractions is going to give, divided by n, is going to give me alpha. And if you think about the p's and the q's, you can also convince yourself that it makes sense that this is the estimate for p, and this is the estimate for q. Here you're summing over the sum of the P1i's over all the data points. And here what you have is a weighted P1i, weighted by hi over m, the number of heads that you've seen in a given data point. And the same thing for the other one. So basically, what we've shown so far is we're given two parts of the algorithm. Step one was we're looking at the data and we're labeling it. How do we label it? We guess a set of parameters, and given this set of parameters, we assign labels to the data. These were the P1Is. P1Is are labels, fractional labels. Now that we have P1Is, and we have the old P, Q, alpha, which I'm denoting here as P hat, Q hat, and alpha hat, I can update my estimation for the parameters, and I can keep on going. So this is really the same naive Bayes algorithm that you are running in your experiments, and it's the same naive Bayes algorithm that we described earlier, where you had 100 unlabeled examples and you wanted to use them. Okay? You label the data, you make predictions using these labels, and you relabel and so on. Okay. Questions? Well, this is stuck here. Nice. Okay. Okay, let's try again. Okay, so again, since we are here, I want to remind you, this is step one of the algorithm, which is called the expectation step, which you can think about as the labeling step. And then we do a little bit of math, and we derive the update step, which we call the maximization step, because we are maximizing the likelihood of the data. And this gives us update rule for the parameters. Okay. So, okay, so that's EM with another explanation. Now, as I said, EM is a general procedure. I don't necessarily want you to understand the general thing, but I want you to understand what is EM. So it's a general procedure for learning in the presence of unobserved variables. If you remember when we talked about decision trees, bringing you back a couple of months earlier, one of the questions that I asked at some point is, how would you deal with the cases where you have missing variables? I'm giving you an example, and you want to evaluate your decision tree, or you want to learn a decision tree, but some of the features are missing. And the question is what to do with it. And we gave several options. Some of them were just, just put a value there. And some suggestions that you've made were look at the rest of the data and try to learn what would be a value that makes sense to substitute for the missing feature. Essentially, that's what EM is doing. Only that now we are guessing the substitute under a very specific probabilistic assumption. We guess the P1I in a way that depended on our assumptions on the model that generated the data. That's how we computed the P1I. And therefore, we can prove that actually this makes sense. In fact, what you can prove is that if the data really is generated according to the assumption, every step of update increases the log likelihood. And therefore, we're going to converge to a local maximum of the log likelihood function. Okay. Again, it's important to realize that we are assuming a family of probability distribution. Sometimes when you look in the literature, people will tell you, we use the M. And then you have to realize, well, they didn't give me all the details because they didn't tell me what probabilistic assumption they've made and what exactly are the update rules for the parameters, these rules that they used. So you need a little bit more details than just we use the M. Okay, so EM is actually a very, very good algorithm once you make good assumption. And what we've shown here is we've shown it in the case of mixture of Bernoullis, right? Coin tosses. I'm going to show it in one other setting, which I think is very interesting. And this is going to give us the k-means algorithm. Anyone heard about k-means? No one heard about k-means? 1, 2, 3, 4. So what is k-means? Can someone say something? Yeah, suggestion there. What is k-means? You wanted to say something? No. Yes?
You're trying to break up the set of data points into k groups that are as close to each other as possible.
Exactly. So I want to cluster. I have a set of points. Someone told me they come from k different clusters, collections. And I want to take these data points and cluster them into these k groups. That's k-means. How would I do this? Anyone knows how this works? You want to suggest something? Go ahead. Yeah.
I think you randomly pick groups and then sort each data point into its closest group. And then you calculate the mean point of each group and then iterate again until there's.
Yeah, excellent. This is exactly the algorithm. So you actually gave us the pseudocode. I'm going to write here the pseudocode, which you just said. So the standard k-mean clustering works this way. So I know that I have k clusters. So I'm guessing k centers. Once I have k centers, I'm placing the data points into them in a greedy way based on distance. So each point chooses the closest center and says, I belong to your center, to your cluster. Now I have k clusters, and I'm going to re-estimate the means, the centers. So the centers are going to change again a little bit. And then each point is going to ask itself again, which center do I belong to now? And again, it's going to place itself in the center given the closest distance. And we're going to repeat. Very simple algorithm, very intuitive algorithm. Works beautifully. What we're going to do today is we're going to show that this is really an EM algorithm. Hopefully you already see this from the structure of the algorithm, and we're going to give an improvement to this algorithm. Again, read the pseudocode. It's a very simple and nice pseudocode. You know that there are k centers. You know, that's an assumption here. Each point, so you guess the k centers, random guess. Now each point chooses the center it wants to belong to. Think about the centers as the labels of the points, okay? 1 to k labels. So each point decides, I like this label. Now you have k clusters. And you re-estimate for each cluster its best center just by averaging, and you continue. Okay, so this is the picture that you can imagine if we are on the line we have endpoints, we have 2 centers in this picture, and you can see that it's a tough problem to decide. I told you that these points were generated in the following way. First, choose a center, mu, and then, assuming that we have Gaussian distributions, generate a point with a mean mu, and we're going to fix the standard deviation for all centers to be the same, for all clusters to be the same sigma. So this is how the data was generated, and you want to reverse engineering to figure out what are the mu's. Okay, so again, just like we did before, if we knew, just like in the coins, if we knew that all the data points are taken from a normal distribution with mu as mean, you know what's the most likely value of mu. What is it? Here's a set of data points. I told you that they are taken from the normal distribution with mean mu. Give me mu. What is mu? Yeah? Just the average. Mean, average, it's synonym, right? Now, why is that the right thing to do? In addition to the fact that mean and average in some contexts are synonyms, in this class, the justification that you should give is it's the most likely value. Right? That's what we're playing here. And it is the most likely value, and it's very easy to see, because if we say that it's coming from the normal distribution, the probability of x given that the mean is mu is given by this expression. Forget the constants in the front, it doesn't matter. We're going to compute the likelihood of the data now that we have m points. The log of the likelihood of the data is given, I have sum over all data points, sum of all the data points. And then when I took the log, I just stayed with this expression. And then I'm going to differentiate it and maximize relative to mu, right? So I want to minimize this. This is, again, the constant doesn't matter. And if you equate this to 0 and you solve, you get that mu is surprisingly the average. So this is the right thing to do under the normal distribution assumption. May not be the right thing to do if you assume something else, but we assume normal distribution. So that's an easy problem. If I told you the mu's, you know what to do. The problem is that we don't know what the mu's are. These are the missing variables that we have. So just like in the coin problem, the problem is that the data is sampled from a mixture of k different normal distributions, and we don't know for a given data point which mu it's coming from. So that's what we're going to do. So we're going to play exactly the same game as we played with the coin before. Assume that we look at the ith data point, xi. We are asking what's the label, right? Which coin it came from, or which mu it came from. And we're going to compute the probability that xi, the ith point, came from the jth center. Pij, in this case, is going to be the probability that it's the jth center that generated the ith point. Let's compute it. Again, Bayes' rule says that P mu j given xi is P of xi came from mu j times P of mu j divided by the probability of the data. I'm assuming that all the mu i's are equally likely. So it's 1 over k times P of xi given mu j divided by the probability of the data, that is basically sum over all k's of P of xi given mu j times 1 over k. So now I know that this one is normal, so I'm writing it here. And now I have a little bit of math again that I have to deal with. And in order to easily deal with this math, I'm going to introduce a set of variables that I'm going to call here Zij, Zi1 up to Zik, for K clusters. Zij are going to be Boolean variables. Zij is 1 if xi came from the jth cluster. Otherwise, it's 0. Okay? So basically, so one of them is 1. All the rest are 0, basically. Notice that when I'm thinking about the Zij, it's a Boolean variable, and therefore the expectation of Zij, what is the expectation? It's 1 if xi came from uj, and it's 0 otherwise. So the expectation of Zij is Pij. Okay? That's always the case. And I'm also reminding you in red fonts here that expectation is, what is the expectation? And that expectation is linear. The expectation of the sum is the sum of the expectations. And once we have this, I can compute now the probability that y, the label came from, the data came from this hypothesis. So what is my hypothesis now? What is the set of parameters that I care about? I care about sigma and the mu i's. These are the parameters. So I'm writing it now in terms of the z's. I care about the probability of x, comma, z1, zi1 up to zik, given my parameters, and I know how to write it. I know that it's a normal distribution, so this is just substitution here. And now I can compute the likelihood of the given observation of the data given these parameters. Exactly the same thing as we did before. Log P of y given h, I can write it as sum over all data points. I already took the log, so I have sum of these expressions. The expectation of this, I'm doing the same cheating as we did before, is the expectation of this sum. And there's really just a simple algebra here. Okay, so now I have to maximize this relative to the mu's. I'm denoting it here, it's Q. Q of the new set of parameters given the old set of parameters. And I'm differentiating it relative to Q and to mu, and this is what I get. So again, I have some constants, sum over all data points, E of Zij times this. I want this to be 0, and that's what I get. And again, let's look at it and see if it makes sense to us. This is just reminding you that H prime is the old parameters that we assumed. But more importantly is that we look at this mu and see if it makes sense to us. So essentially, remember, E of Zij is basically Pij, the probability that the ith data point came from the jth cluster. So what we got here is we got a weighted sum of the data points, a weighted average of the data points. And that's how we get mu. Okay, so let's before we summarize this, we had two steps. The first step was estimating Pij, estimating the label of each point, or estimating the cluster into which we place each point. And we call this Pij. Pij is the probability that the ith point came from the jth cluster. And we knew how to compute it. Once we computed this, we could estimate the new mu. So let's now go back to the simple description of the algorithm that we had before. This is the algorithm, right? So before, when we describe k-means, we said each point, we guess k-centers, we guess initial parameters. Each point places itself in a cluster, chooses a cluster. Now we compute, now we have k clusters, each one of them has several points. We recompute the centers for each clusters, and we keep on going. What is the difference between this algorithm, this pseudocode that I've written here, and the algorithm that we have here? You also have these two steps, right? So you have this computing Pij, step 1, and computing the centers, the μj. What's the difference between the two? Any suggestion? Yeah?
Guess the parameters, but we don't guess the cluster centers for the initial point.
What do you mean? The μ's are the cluster centers. So that's what we guess. Right? We cannot compute Pij without having the initial μ's. Right? So we do guess k-centers here, and we do guess k-centers here. Yes?
It's how we assign each point to a different mean. In the first version, we just did it on based on what it was closest to, and now we're assuming something probabilistic.
Right, so that's the key step. So here we said each point chooses a center based on distance. So if I'm a point, I'm choosing one of the centers. 1 up to k, I have to choose a center. While here, if I'm the ith point, I'm choosing the jth center with the probability Pij. So in principle, I can choose all centers. I'm 0.1 into center 1, I'm 0.3 into center 2, I'm 0.5 into center 3, and maybe 0 for the others. So fractionally, I'm choosing which center to belong to. And this is how I do it, based on the normal distribution. Right? So this is the denominator here is just a normalization factor. So I'm doing it this way, based on the numerator. So the issue is, it's a fractional labeling. Each point now has a label, but it's fractional. Go back to what we've done at the beginning and last time with the points and the n and the v, right? So you took a point, and the initial parameters, the guessed parameters, or the initial parameters based on the 10 example told you, oh, I'm going to predict this to be an n point or a v point. And what we suggested as an improvement is don't predict, but rather predict fractional labels. Allow a point to be 0.8 n, 0.2 v. This is what's happening here, right? So each point allows itself to be partly in center 1, partly in center 2, and so on. So that's the Pij. So Pij do not necessarily have to be 1 for one of the j's and 0 for all the others, but they could be fractional. Of course, they sum to 1 by definition here. And then, so this is the first bullet here. And then we re-estimate the centers. That's exactly the same thing as we've done in the classical k-means. Essentially, it's an average. And these mui's here are also averages, right? So it's if EZij is only 0 and 1, it's exactly average. Once it's a fractional number, it's a weighted average of the points, right? So consider each part. If you're looking at the first center, consider for each point the fraction of it that belongs to my center and average. That's what we're doing. So essentially what we did is we improved the classical k-means by allowing fractional labels. That's it. Okay. Questions? Yeah.
Do your initial guesses at all influence what you end up with?
Yeah. So EM and k-means, which is an example of EM, are finding local maximum of the likelihood function. So it's going to matter. And the way people run EM is they would initialize it many, many times until they're tired and they stop with the highest value they found. Or if you have some idea, you can initialize using these ideas, your understanding of the problem. So if you know how to initialize it and if you made the right assumption, it's actually a magical algorithm. Okay, so here's a summary of EM. There are a few more slides on EM, running EM in a couple of models, and one interesting question here that I suggest you look at. I'm not going to spend time on it now, but I think it's an interesting example that allows one to think at the same time on discriminative learning and on probabilistic learning. I want to stop here, unless there are additional questions, and move to our next and last chapter, which is going to be talking about probability distributions and learning probability distribution in a slightly more general way. Yeah.
For naive Bayes, just in general, how is it normally represented? So like on the homework it says, using things you calculated and write down a naive Bayes classifier, but like how do we represent that as a single thing?
So what do you want to represent? What do you have when you have a naive Bayes classifier?
Have all the conditional probabilities, I guess.
Yeah.
So is that
Why is that a better representation? Right, so you have a bunch of conditional probabilities, and that's your model. Yeah. So typically you'll represent the log of these, but basically that's it. So it's equivalent to having a bunch of weights when you have perceptron or SVM, right? Think about it also as a bunch of weights that you computed from the data. Okay, so so far we talked in general about Bayesian learning. We talked about naive Bayes, which is the most important instance of this, and the independence assumption that led to it. And we talked about EM. And I want to generalize this a little bit to talk about more general probability distribution, a little bit about inference. We're not going to talk about inference. I'm just going to say what it is and give an example of how to learn a representation, a more general representation of a probability distribution. So that's the game we're playing now. We're thinking about it from the unsupervised learning perspective, right? So we have data points. We don't have a notion of class label. We see examples, and we want to learn a representation that could have generated this set of examples, or the most likely representation that could have generated this. Sometimes you'll see it called density estimation. Now, we can think about what we've done before as an instance of this, right? So this is what we've done when we did a naive Bayes, right? So we had variables, x1 up to xn, and we also had y, which was the label. So n plus 1 variables. And what we've done in the last few minutes basically was to learn a representation for this kind of distribution. This is a naive Bayes-like picture. You first generate y, and according to the value of y, you generated the xi's according to the probability p of xi given y. Now, this picture already hides an assumption. The assumption that it hides is that p of x, that xi and xj are independent given y, or I'm writing it here as p of xi given xj and y is the same as p of xi given y. You should be comfortable with this. This is another way of saying that xi and xj are independent given y. Okay? So this picture actually hides this conditional independence assumption. What we're going to do today is we're going to generalize this to more general graphs that will also hide an independence assumption. So we're going to think about slightly different assumptions that will allow us to encode and learn more general probability distribution. Okay, so what have we done with naive Bayes? We basically given these parameters, right? So n plus 1 parameters, if you want, p of y, and then all the conditionals, p of xi given y. We knew that we can write the joint probability distribution, right? We can write p of y, x1, x2, xn as this. You have to make sure that you agree with that. If not, think a little bit about it and realize that we know how to do this, right? So that was really the naive Bayes assumption. It allowed me to take the joint and decompose it this way, right? Now, notice that once I agree that this is the case, I can take any event. For example, I can take the event x1 equals 0, x2 equals 0, y equals 1, and compute the probability of this event, right? When you have the joint probability, the probability of all assignments, x1 up to xn and y, as I've written here, you can compute this. How can you compute it? Well, the standard way to do it is to marginalize. Basically to say, okay, I know what x1 is, I know what x2 is, I know what y is, I don't know what all the others are, so I'm going to marginalize over all the other values, x2, x3, x4, up to xn, and I'm going to sum over this. That's a generic way of doing it. How long will this computation take? How many elements are in this sum? Look at it. How many elements are in this sum that I've written here? So there are n plus 1 variables. 3 of them are fixed. I'm left with n minus 2 variables. Each one of them can take 2 values. B's, the b's here would be 0 or 1. So I have 2 to the n minus 2 elements in this sum, right? But that's the generic way to compute the probability of events. Okay? You've seen this in any probability class that you've done. Now, you don't want to do it this way, right? Because you don't want to sum 2 to the n minus 2 numbers. And in this case, you don't have to, because directly from the independence assumption, I can write it this way. I can say, oh, you care about p of x1 being 0, x2 being 0, y being 1. Let's decompose. It's p of x1, x2 given y times p of y. I know p of y. And I can also decompose, continue and decompose this to be p of x1 given y times p of x2 given y times p of y. And that's because of the independence assumption. In general, I cannot do this. In general, I have to do the marginalization, the one that has so many elements in the sum. Okay? Okay, so now this is something that we can do for naive Bayes, and I want to be able to do it in a more general way. for other probability distributions. So I have to agree on a representation language for probability distributions. Here is one way to represent a probability distribution. If I have n variables, let's assume they are Boolean variables. I have 2 to the n configurations of the n variables, right? I can assign each one of them a probability. And I have a representation of a probability distribution over n variables, a table. Now, I'm writing here that we need 2 to the n minus 1 numbers. Why is that? Why not 2 to the n numbers? Okay, I'm assuming that you're just shy and you know this, because these numbers have to sum to 1, otherwise it wouldn't be a probability distribution. So, so that's a most general way to represent distributions. As a table, discrete distributions, 2 to the n minus 1 independent variables, independent parameters, and that's it. Now, this is probably not the best way to do it because it's too large. And therefore, we're going to invent other representations that encode one way or another independence assumption and provide a more compact representation as a function of it. Remember, if you go back to the naive Bayes thing, this is also a probability distribution over n plus 1 variables. And you could have said, oh, you need 2 to the n plus 1 minus 1 parameters. Take n to be 10, 9, it would be easier. If n is 9 here, you need 2 to the 10 minus 1 parameters to represent all the probability distribution. How many parameters do we need here under the naive Bayes assumption? A lot less, right? Do the computation. It's order of 9, right? Some constant, small constant times 9. A lot less than 1024. And this is the idea here. Now we also want to represent it in a more compact way. And there are multiple ways of doing it. And what we're going to focus on is on Bayes nets, Bayesian networks, as a representation of a probability distribution. So Bayes nets are directly acyclic graphs. So they look something like this. And they also have an assumption, the same kind of assumption that we had for naive Bayes, just slightly more generalized. The independence assumption is that for every variable x, x is independent of its non-descendants given its parents. Okay? So z here is a parent of x. So x is independent of y given z. X is also independent of, no, that's it, of y. X is a descendant of y here. And therefore, what I said is right. So it's independent of y given z. And with this convention, I can write down the joint probability distribution in a way that is similar to the naive Bayes, slightly more general. I can say that the joint probability distribution is P of y, which is the only variable here that has no parents, times P of xi given the parents of xi. So essentially, it's the product over all variables, P of variable given its parents. Now, this is a theorem. You can easily prove this theorem given these assumptions just by ordering the variable, choose an order of the variables, and decompose the probability distribution according to this order. And use this assumption that x is independent of its non-descendants given its parents, just like we did for naive Bayes. So that's the key thing that I want you to know. These terms are called conditional probability tables, CPTs, and they define the probability distribution. So once you know the conditional probability of xi given its parents, you know the probability distribution. Remember that this was the case also for naive Bayes. So What we're going to do is we're going to take this and play with it a little bit next time, understand the semantics of this, look at a few examples, and give one example of how to learn a probability distribution like this, a specific case of BaseNet. Okay, see you Wednesday.
I have a question regarding the homework.
Yeah.
So the value of k for low-pass smoothing doesn't really affect the accuracy of the overall 20 classes as much, but it affects the accuracy per class. So let's say when I have with different values of k, let's say for one of the classes, I would predict it wrong more often than I don't.
And when you do average over all of them?
Average all of them is roughly the same. So like if I do 20 classes, it's roughly like 60%. But let's say alt atheism, if I have a large value of k, let's say whatever number it is, let's say 2, for example, 1 or 2. Alt atheism has like 30% accuracy, like, for example. But then some other classes have higher ones. But when I have like a lower value of k, like in order of like 0.001, like a pretty small value of k, autism gets like 55% accuracy, but the other one also like decrease. So overall, the average would be the same. Roughly is like 60%. Over all classes, do you know why that is?
It's probably the case that specific prediction in this class, because the feature values are sparser or something like this, are misbehaving, basically. So can you look, how many examples are in the test for autism?
Or for autism is 360 something documents. Overall is 7,300, something like that documents for all tests. It's roughly pretty much the same on each folder. So it's not like one of them has like one more.
So again, what's the difference that you see from 55% to what?
So it goes, so when I do K1, which I think is like a normal value they use, it's like 27% accuracy autism. It's pretty low. But the other ones have like very high accuracy. So let's say like computer, there's like computer graphics, for example, has like 90% accuracy. It predicts that like pretty well. But roughly on average, it becomes around like 60% accuracy on all 20 classes.
Yeah.
When I do K way lower, so like 0.0001, I just want to see like what happens.
Yeah, no, it's actually a very interesting question. I don't know. This is something to do with the data. Actually, it would be interesting if you can figure it out.
Yeah, because like all the ATS,
so
for example, goes to 60%.
I did not know that this is happening when you play with values of k.
Yeah.
So just take your class. So you think that it's all due to this specific class?
I was thinking of this, I don't know if it makes any sense. So K is, in the case that a word does not exist in that specific class, you put K equal a number and then divide it by whatever. The denominator is always the same for each class. It's like the same denominator. But numerator changes based on if the word exists or not exists. Right? So if a word does not exist and K is really high, you are giving it a high probability saying that that word does not exist. You want that number to be close to 0, right? So I assume that if k is very small, it's better than being large. Like, I just feel like I don't understand why k. I guess what I'm saying is k would matter what value of k is to what prediction you get, because I think the value of k would.
Yeah, but you're doing it uniformly for all words.
Yes, but let's say some of the documents, let's say we have a set of vocabularies, right? Some documents may not have a lot of words. Yeah, so some documents may have like, I don't know if I'm making, so yeah, some documents may not have a lot of words. So that number you put k would really affect it, so like it would completely throws it off. Because it's k over...
No, I think you're right. So the common belief is that in more complex probabilistic models, the way you do the smoothing matters a lot. And there's been studies on that. And that for naive Bayes, it doesn't matter so much. So basically what you're saying, if I have extremely different sparseness
on
basically
one of the
among
classes.
the labels,
Yes.
among the labels of each class. So one class is more sparse than others, then it will make a big difference.
Yeah. It's just that odd atheism seems like there might be a lot of words.
But if that's the case, then it means that you could probably find a value of k.
Yeah,
that is
I was trying to.
optimal.
It's just like so hard. It's not that fast to run all of this.
No, without, I mean, can't you do this analytically? So essentially what you're saying is that, let's say you knew how many variables, how many features each class has, and how many of them are missing in the test. That's actually a big assumption, the second part of what I said, because you haven't seen the test.
I haven't seen it. I don't know
But
what
once you see the test, you could estimate it, right? So you can see how many features are there that you've never seen in training.
that I've never seen it. So my assumption is there are a lot of words in tests for all atheism that I do not see.
Right, and in other classes, you think that you don't see a lot of new words.
Yeah. Because it kind of makes sense. Computer graphics, for example, the terms are pretty limited. I mean, you can't really discover it very much.
I think it's a nice point. So actually what you're saying, as a function of rate of new word appearance per label, maybe you can tune k and get an optimal number.
I can try to do it.
Yeah, right. Very, very interesting. Actually, I don't know if people have done that.
Hey, do you mind
No,
if
I mean, I was just wondering.
towards the beginning?
I was getting very low accuracies for getting accuracies for all classes, and for some reason autism is always very low. The other ones are really high. But autism is always low. I just went like a really low K, and that became like 60% accuracy.
Yeah, I think it's a very interesting thing. So you can try to play with it and see if you can even write some down.
Which one is better though, to be able to predict classes roughly the same accuracy,
So that depends on your loss function. Right? So in some situation, you care more about some labels than others. In our case, we didn't tell you it's uniform, right? So it doesn't matter. But you could imagine a situation where some of the labels are more important.
and based on that you can decide what your value should be. Makes sense.
Good, thanks.
All right, well, we've got about half the class here right now, but we will be doing Lesson 2 presentations. The order today will be going from the bottom up of the list of groups, unless there are any groups who'd like to volunteer to go ahead of time, other than the one group who started contacting me. Okay. All right. Let me see.